Okay, so today we're talking about section 5.3, which is differential equations with growth and decay. So these are the ones kind of like carbon dating or radioactive substances getting larger or smaller, things like that. And so that's kind of what the math is that we're going to be doing here. So talking about a few things here, let me pull up the slideshow and I'm going to skip through a few of them. There's 25 slides. There's some I'm going to spend a little more time on, some I'm just going to go through because they're not as pertinent as others here. But a little review here just to kind of remind you of our derivatives and our integrals, going back both directions here. So looking at the examples here on the screen, we've got a couple of derivatives. And as you see, they call them differential equations. Derivatives, dy dx, or the y prime. These are the derivatives right there. Okay, so differential equation is obviously something that has some derivatives in it, something like you see these two examples right here. Some definitions, because you are going to have a homework problem or two like this. First order differentials has a first derivative, nothing higher. And like these examples here, second orders you're going to see have second derivatives, this y prime prime. So there may be a first derivative, but it's sort of like what do you call it? The degree of a polynomial is the highest power on a differential equation. Whatever the highest or the biggest differential derivative, that's going to be the order that we have. So these are first order differentials on top. This is a second differential, even though it's got a first derivative. It's whatever the highest one is. Okay, so solution, we've kind of done that before here. And this is back to algebra here. If you have a differential equation, you substitute something left and right side if they're equal. If you get the same thing, that's how you know if it's a solution. All right, and this is the fun part, difficult or impossible. Some of these are going to be really tough, but I'm going to go through and show you kind of the process, how we do them here. So here we have a regular equation, y equals 5x minus 19, and they ask, is this function a solution to this differential equation right here? Okay, so a couple parts, steps that we're going to do here. So first off, if you see it's, again, I don't like the commas here, but if you take the derivative of the original, this equation right here, take the derivative, dy dx, you get a 5. Okay, so I would write this below, but if you have y equals 5x minus 19, the dy dx equals 5, just like that. So if you treat this dy dx just like it's another variable, like an a, b, c, or whatever. If right here dy dx equals 5, put a 5 in right there and see what you get. So on the left side of this equation up here, it's x minus 3 times dy dx. So when you replace it, you get x minus 3 times 5. So the left side becomes 5x minus 15. Okay? So then on the right side of this equation, this y plus 4, you're essentially going to replace the y with the 5x minus 19. That's what happens right in here. So, I'm not a fan of the left right, but that's the way you're kind of getting taught this in the book. So I'll give you kind of the alternative, but this is what they mean. The left side and the right side right here. In the left side, you replace this right here in place of that. That's how they got this. And the left side's a 5x minus 15. The right side, which is this, you replace the y with the original equation. So that right there becomes this. And that's how they get this 5x minus 19 plus the 4, that 4 right there. And then when you simplify that, you get 5x minus 15. So if you get the same thing on both sides, that's what they mean by, something is a solution. Left and right sides are equal, therefore the original equation is a solution. So, if you think about it, back when you first learned equations, you were asked to plug in numbers. Is x equals 5 a solution to this equation? You'd plug in 5 in place of x and see what you get on both sides. It's basically a couple levels higher now, where they give you this and they tell you this information, and this is what you're plugging in. But instead of a single number, you're plugging in a whole equation. You're finding the derivative of it, and you're using all of that. So that's the procedure that you're going to be doing on a couple of your problems when they want you to check if a function is a solution. Just plug in the pieces, and the trick is, does the left side equal the right side? Okay, so now we're going to talk about these things called slope fields. And these are very interesting because what's going to happen is you're going to start to get derivatives that have more than one letter. Like this one has a y. Sometimes you're going to get x's in here. Sometimes you're going to get y's and x's. And what it's, again, don't forget, the derivative is telling you slopes. Okay, that has not changed. The slope of an equation, the tangent line, I'm sorry, the slope of the tangent line at a given point. But when you have derivatives or functions that have x's and y's, you got to see what you're plugging in. So I'll talk about it and show you what we mean by when we plug something in here. So you read this next statement. It's a solution if it satisfies an equation for all values of x in the domain. Okay, so that's kind of something you already knew, but let's get to the actual problem here. All right, so they're just kind of defining some things right here. We have a first order differential equation, dy dx equals 0.2y. All right, so if in that differential equation, if a function is a solution, then the equation gives the slope of a solution curve that passes through the point xy. All right, so it's kind of a weird one, but it's similar to what we did just now. So kind of see what's happening right here. All right, they're asking, if this is a solution that passes through the point 0,2. Okay, so they're saying it is a solution that passes through the point 0,2. Then the slope of it is going to be that down there. Now, where do we get this point 0,2 from? Okay, what's going to happen is it's supposed to work through pretty much any point of the function that we have here. So what I want you to see right here is whenever you have a given point, you know, in the past we would plug in the x into the derivative equation. Well, in this particular point, we don't have, this particular function right up here, we don't have an x, but we do have a y. That's what we're replacing in place of this y. And they're saying at that point, the slope of the tangent line is going to be 0.4. Okay, so that part hasn't changed from what you did before. It's just that you're plugging in different variables. So anytime you have a dy dx, like this one on the very top, you're going to be given a bunch of x's and y's, a bunch of points. Really, this could be for any point. That's the deal. So if we have this point 0,2, you go and you plug the x's and y's. If you only have y, just plug in the y and you see what the slope is. And that's how we're going to build this, what they call the slope field. So now we're going to do the same thing at the point -3, +1. Back to this equation again. You're going to replace y with a 1, and that's how they got the slope at the point -3, 1 is going to be 0.2. So the deal is you're going to keep plugging in a bunch of points, mix them up, and try to get a summary of where the field is. So here's another point. You replace the y with 3, you get 0.6. Now, looking at the 3 points we've tried, where is it? 0,2 is right here. -3, 1 is right here, and 2, 3 is right here. So these are the points. What they did was at all 3 of those points, they plugged them into this derivative to get the slope right there, the slope of the tangent line. So that's why they have these little hash marks, these 3 red hash marks. If I can erase that, sorry. These 3 hash marks right here, they represent the slopes. So again, you see at the point 0,2, the slope we got is 0.4. That's this line right here. If I continue on, that has a slope of 0.4. Okay? At the point -3, 1, you have a 0.2. So all I want you to see is it's positive slope. It's not as slanted as this one, but it's still a positive slope. Just like this one is even more slanted, and they're trying to get us to build a pattern. So the collection of all of these is what's known as the slope field. All right, so I'll show you another one here. So a possible graph of f is sketched through these 3 tangent lines. There's a picture right there that could flow right through all of them. Okay, now there's a lot more. Now, you see here, it goes to this kind of crazy magnetic field looking thing. If we continue the process of drawing tangent lines, so what they're doing basically is they're taking every single coordinate here, 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 and so forth, and they're just plugging in all of that back to, where was it? This equation right here. You just keep plugging in points. Now, thing I'll point out right now, notice this derivative, as we mentioned, it does not have an x value in it. So what that means is it doesn't matter what the x value is, it's always about the y. So you see here when I plugged in 0, 2, I only looked at the 2. I'm getting the same answer if I plug in 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, negative 5, 2. Basically, anything here on this line, they're all going to have that same kind of a slope because it's only the y value that matters. Just like down here at positive 1, they're all going to have this slope. And that's pretty much how we arrive at this picture of this slope field, right here. So you kind of see in a line, every one of these right here, they all have the same slope. All of these have the same slope. All of these do, and these do. That's your consistency, and that's what happens when there is no x value in the derivative. So you just have to get a few, and you're trying to gauge the pattern of what's happening. What's going on as you find more and more slopes of the tangent lines as you get more and more, plugging into the derivative, all these different points. So there's an example of a function that may fit, and they're asking you, okay, they say we guess the solutions were exponential functions. Now, that part's not always as easy to see because there's just, what you have to realize is, let me go back to this picture right here. You're trying to draw a function through these lines, but obviously I can't go and draw through each of these lines because it's going up and down. So you have to look at it as, well, if I'm right here, it's rising up and it's probably going to hit one up here, hit one over here, hit one over here, and so forth. You want to try to make a path that goes through some points, some slopes following that same kind of angle. And that's the idea right here of just trying to draw, or for now we're just doing the slope fields, but trying to summarize what's happening with all of them. Okay, so they say the one highlighted suggests solutions to, our exponential functions. It's not 100% apparent to see, but if you were to keep going up and up and up here, these slopes are definitely tilting upward. We just don't have enough space to show it here. And that's how they're able to sort of conclude that we're getting an exponential function. Okay, so now we get this one. This is something that you're going to see a lot. This sort of equation right here. What it's saying is there's going to be some sort of an exponential function. It doesn't necessarily have to be e, but it's going to be something that we have here. Okay, now how do they get this? I'll tell you right now. This is what, you've seen this a little bit before. This is your standard sort of exponential function. The base could be different things on other exponentials, but e is our kind of our winner, our main one that we always use. So what we're looking at here is they're trying to show, okay, we guess it, we want to show that this is the solution to the differential. So this is like what we did a second ago, left side and right side. The left side is just the derivative. So take the derivative of this, and that's what they're doing, and you get, with the chain rule, 0.2, CE to the 0.2x. That's the left side. Now we do the right side where we have this, and we take an equation, and we're going to replace it there. Well, follow what they do here. If we know y equals all of this, that's going to replace right in there. And like we did before, if you get the same thing on both sides, then you know it's a solution. Now, you don't need to come up with that solution just yet. Okay, we'll get to that later on, but right now this is just a case of checking to see if it was in fact a solution. Again, you'll see this on one homework problem, I think, maybe two, a couple, at least a couple we do today here. All right, now the practical side. This is where it gets interesting. So they talk about this 20 by 20 grid would have 400 tangent line segments because you're doing one in every row, 20 in every row, and it's got like 20 columns. And this is not going to be easy, and this is where they say it's going to be left for the computer or calculator technology, but we have to understand what it means, how this is all working. All right, so now we'll get to the main core of what matters in this chapter, these continuous compound interest. If you've ever taken a business math class, you've dealt with compound interest. In this particular case, it's a little different. It's continuous. So in normal times, you have interest that's compounded monthly or quarterly or yearly, semi-annually, even daily. What a compound interest is, it's always calculating interest all the time, continuously, every nanosecond of the day. And it is going to have an exponential growth, and we're going to figure out how to find that. And what this is that they're doing is they start with these problems, and then it helps you kind of understand it when we start dealing with, the half-lives, the radioactive substances, the carbon dating. They're all in the same ballpark here. Okay, so dA of dy, remember, is the rate of growth of A with respect to t, some t, and we have, and that's supposed to be a t right down here. That's a little PowerPoint mistake. It's supposed to be a t right there. Sorry about that. So dA dt is equal to r times A. All right, you've had that a little bit before. It's some constant just saying that this is the rate that's affecting it, some r that we don't know of yet. A of 0, so whenever you're plugging in, t is your time. Okay, that's your variable. This is what it normally looks like. It's the time right there. So when you get time as 0, this basically means P is your principal. It's what you start out as. So it's always going to be that right there. Okay, so now we have to come up with a function that satisfies these conditions. So look at where we're at here. We have all of this, and it's a lot of algebra, like a lot of things here. You're going to see the process, and then again, we'll emulate this later on when we do some homework. They want us to multiply both sides by 1 over A, because what we're doing is we want to solve for this R right here, okay? We want to isolate that R because we're trying to find that here. So we're going to integrate both sides. We're going to integrate this side with respect to dt, and we're going to integrate the right side with respect to dt. And the reason is because it's time. It's always about time. Now, the part that's quirky is they won't show it. They did show it. Okay. Basically, these dt's are like regular numbers or variables. They cancel right off. So we are left with an integral that's with respect to a on the left and one that's with respect to t on the right. And we're going to integrate both of these two separate problems. So the one on the left is going to be a natural log of a, because we know that one. The one on the right, because we're integrating with respect to t, remember, treat r like a constant. They even said it was a constant before. So all we do is we put a t right there, r times t. It's just like if I was integrating 5 dt, the answer is 5t. Well, instead, we're integrating r dt. That's why my answer is rt right there. And of course, you still have that plus c that we're always dealing with. So what we've essentially done is we've integrated to come up with a better formula to try to figure some things out here, some facts about what's happening. Okay? So A equals RT. Now, this is an interesting part. They told us earlier that A has to be a positive number. Okay? It's the amount, the balance that you have. It's always positive. That's why you're never going to have to worry about a negative number in here. So that's why they just essentially dropped off the absolute value sign and said natural log of A equals RT plus C. Now, little recall here. This is just sort of on the right, the y equals natural log of x. It's like the definition of what a natural log is. And those are the two different forms that mean the same thing right there. Okay, so if you take your equation, you can do this thing where, let me write this out. If you have the natural log, get this here. You have the natural log of A equals RT, R times T, not to the T power, RT plus C. Okay, if I'm trying now to get the A by itself. So in order to do that, the easy fact is I can just simply go and put an E right here. And E becomes the new base. So it's like I'm taking both of these things are equal right here. They'll still be equal if I make them both powers of E. The reason I do that is if you have E to the natural log, it just simply cancels out. And then you have E to the RT plus C. So we're doing lots of algebra in this section, in these last couple sections here. Okay? So what happens then is, this is an old fact that they reminded us of, A of 0 equals P, so P equals, what I'm going to do is I'm going to plug in in place of A, I'm putting in this P right here. And you can kind of see it here. Let me erase this so you can just see the printed version. And because I know that's equal to P, it's when T is equal to 0. So we take this equation and you replace the T with a 0. That T right in here. Okay? So how they got from here to here, let me make sure everyone understands that. That's the old rule of exponents. If you have x to the fifth times x to the second, remember how you add the exponents to get x to the seventh? Well, it's the same thing when you go the other way. If you have two things added together in a power, you can just rewrite it as the e times the t right there, e times e. And you get that. So we plug in a 0 for t right here, so we get an e to the 0. And you should remember that e to the 0 is just a 1. So now we're left with just this. P equals e to the c. All right. Now, all of this, the good news is you don't have to know how to do everything we just did. This is the special formula that you need. Okay, like I said, I spent a little bit of time talking about it just so you can see. Everyone wonders, well, where did you get this formula from? We sort of just now created it, showed you a quick proof. So if you want to see more of it, feel free to go back to the PowerPoint slide and look at it. It's not the most important thing. I just wanted to give you a little bit of a background on how we got that. But what I have right here, A equals PERT to the RT, that's the formula that you're going to use whenever you have continuous compound interest up here. Okay? So how do we use it? What's going on? Well, a couple things here. And you're going to see something like this as well. This is kind of a repeat of what we just saw. A lot of this is the same kind of thing here. But exponential growth is the same kind of object. Okay? It's going to go through all of this exponential growth, exponential decay. What matters here the most is this rate, the growth. So when you have something that has exponential growth, it is growing, growing, growing as time goes on continuously. When it's a decay, it's decreasing. What matters is where that R is, which is going to be eventually your power, but it's the R right here. If it's a positive number, it's going to grow. If it's a negative number, then it's going to decrease, and that's going to be the decay. All right, it'll never decay all the way down to 0. It'll just keep getting smaller and smaller, like half-life, if you've ever heard that. We'll talk about that as well. So population growth, radioactive growth, all these different things, there are a lot of different options that you can come up with when you're doing this. Okay, so now look at a few things here. Sorry, let me pull up another example. Okay, so in this problem right here, kind of read it and look what we have. Population of India in 2010 was 1.2 billion. P is going to represent the population, and T is going to be how many years after 2010. So think of 2010 as the baseline, the start. And we're going to assume a growth rate of 1.5 compounded continuously. And that means basically it's not like in any population, any species, they don't just go like every month we're going to increase our population. As you know, in real life, it's just constantly increasing. Whether it's rabbits or dogs or people, whatever the case, there's a continuous growth always happening. So we want to make an equation, then we want to see what is the estimated population in 2030, and then we want to graph the parts found in A from 2010 to 2030. So kind of watch how this process works here. So we already have this here. So we have this formula right here. Same one we did earlier. Remember that d of something, a derivative, is going to be a rate times the population. And we're given that this is it right here. So jumping right to that formula, remember that A equals PERT. It's a similar one right here is P is going to be the population. This 1.2 is our beginning, our baseline. So the initial population, and I'm going to go back a couple slides just to show you what I'm talking about here. That right there, okay? Yeah, this is for the money, but it's the same thing all the time. Is A equals PERT. Whenever you have a compounded growth, that's what it's going to do. So in this case with the money, the P is the initial, and the A is sort of the end, and the T is how many years, and of course the R is going to be the rate that you're dealing with, okay? Now, when I go to this population problem, it's going to use different variables, but it's the same kind of idea here, okay? The 1.2 is the initial, okay? It was called P before, but as you can see, P is a different letter. This is going to be your population after T years. So if you put 1 year in here, you're going to get the population 1 year later. If you put 10 in there, it's going to be the population 10 years later. And this 0.015, that comes from there, which is the growth rate. What I want to remind you is when they tell you a rate is 1.5%, always remember you don't use percents in these equations. You always have to divide it by 100, to get this 0.015. Sorry. 0.015, and that's the number that they plug in right here. So that's how this formula just sort of happened. It comes from the same one I have on the top right of the screen, but you're using the current factors. And it's going to be the same thing no matter what problem you're dealing with. The rate will always be that R. The T is going to be the number of years, sometimes months or days, depending on the problem. That P, the one right in front of the E, is always going to be the starting number when time was 0. And then it's all going to be equal to this right here, which is after so many years, that'll tell you what the rate is. So that's the equation. It's always going to be based on that. Population equals 1.2 in this problem. Population equals 1.2 e to the 0.015 t. So now they want to know what's our estimated population in 2030. What you have to remember is 2030 is not the time. Okay? Because remember, time was 0 was 2010. So when it's 2011, it's when t equals 1. When it's 2012, it's t equals 2. 2030 is how many years after 2010? That's going to be time equals 20. So that's what we're going to plug into this previous equation on the bottom of the screen right here. We're going to plug in 20 for t. And how did they get 1.6 billion? Okay, and I'm going to show you. Get our calculators out right here. This is what we plugged in 20 for. This can all be done in one step in the calculator. And I want to make sure you know how to do this. Start by doing, the power. I'm going to do the 0.015 times 20. And that is the power of E right there. And if you recall, there's a button right here. When I push this button, it tells me whatever is showing on my screen, that's the power of E it's going to calculate. So I hit that button and I get this. And now I multiply it by 1.2. And you see, this is where they get the 1.6 billion people. Because remember, the population's in billions. They said, yeah, go to the nearest tenth of a billion. That's why it's 1.6. But that's how we get that on a calculator. And that's something that we are going to do many times when, in our homework problems today. Okay, so now they want us to graph the equation we just found. So in this case, yeah, you can use Desmos, you can use a graphing calculator, or you can just remember how an exponential looks. But remember, at time is 0, we knew it was 1.2. At time was 20, we knew it was 1.6. The one we just found, it's not going to be a straight line. These are always going to be exponentials. And remember how exponentials work. As you go out, it's either going to shoot up really quickly or it's going to shoot down really quickly. Obviously, this is a growth problem, so it's going to go upward. And this is all you have to do. This is all they want you to graph. And just remember, it's not going to be a straight line. Okay, that's the only thing to kind of consider on this one. Okay, so another population growth, find the rate of growth. So it's going to be a little different. We're going to find the R. So they tell us that a population, it will double in 100 years. So what that means is, and again, we're using a different formula this time. Whenever you see a 0, that means the start, the initial, the first one, or when time is 0. So when a population is going to double, it means it's going to be 2 times the original, and that's after 100 years. So this formula right here, whether it was the A equals PERT or the Q equals whatever it was, or the P equals QERT, whatever the case, it's always going to be the same formula. And like I just wrote a few minutes ago, this is the initial value, okay? This is going to be the current value after, or the predicted after T years. And then last time they gave us the rate. They didn't give it to us this time. So what we're doing is we're plugging things in here, and let's see what we did. They replaced the t with 100, so that's why it's 100r. P sub 0 is here, and this is 2p sub 0, because remember, it's twice as much as what the result's going to be. And then when you simplify, all we did was we divided by the p0, and that's why you get 2 equals e to the 100 times r, power. Now we have to solve for r. If you remember your good old algebra, or whatever you've taken before this, if you have a variable in the power, in the exponent like we have here, and you need to solve it, the rule is we need to take the log of both sides. So we take a natural log, and why I pick natural log is because it's a base e. So take a natural log of the left, take a natural log of the right, and like earlier, whenever you have natural log and e next to each other, they just simply cancel off. So you have natural log 2 equals 100r. And then we divide both sides by 100, and that's how we get r equals natural log of 2 over 100. And when you plug those into your calculator, you get 0.069, and your rate, if you convert back to a percent, is 0.69%. But this r right here is what matters, the 0.0069. Because what we're going to do, or what we would do in other problems, is you would take this original equation, and now you know the r, and you can replace it with the 0.0069. Okay? So, another example, bone from an ancient tomb. And you've heard this, I'm sure, many times on a History Channel or a news station or anything when they try to talk about what's going on. So what happens is carbon-14, the amount of it that's in a certain substance tells you how old it is, okay? It's a radioactive substance, it's not dangerous to us, but as time goes on, the amount that's in there tells you how old this item is, that, how long ago it was created. So what it's saying was, a bone from an ancient tomb was discovered, and it was found to have 5% of the original radioactive carbon-14 present. So as time, something is made, it has a certain amount of carbon-14, and then when it dies or just sits there, it slowly loses it, and we can estimate it by seeing how much is left and then backdate it. That's how people can tell how old something is, like the age of this bone here. So again, this part I'm going to tell you is not necessary, but what they tell you is they do give you this. And this R, whatever this number is in front of Q, this is your rate, and that's what you're going to plug into our favorite equation. Now you notice you're getting all these different equations. They're all saying the same thing. Here's the initial amount, here's the E, here's the rate, and then it's times a T, and then that's always going to be equal to what the current is. Okay, so this was a given right here. This is essentially the rate for carbon-14 when you date it. So in place of Q, sorry, where are we at here? Q has an initial of 0.5. Okay, I see where they're going here. All right. Let me write it this way. I'm going to show you how you should write it, because I know they're trying to save space on the slides when they do this, but let me clarify this for you all. Okay, so this is don't look at any of this right here. This is the equation. Okay, just like the A equals PERT, they're all the same. They're all using the same bits of information. But so you have all this. What they're telling us is that right now we're left with 5% of the original carbon. So this Q right here is 0.05 of the original amounts. Okay, so I replace this. Remember, our current is exactly 5%, so it's 0.05 of this. Like last time, we divide both sides by that, and we're left with, I hope they'll show it, sorry, this equation right there. So it's 0.5 equals e to the negative 0.001238t. That's just how they got it. I want to make sure you see where they're getting that equation from. So they just replace the current, which is QT, replace that with the 0.05, something they gave you. They had to tell you some sort of a benchmark, some sort of a change. And now our job is to solve for the t. Because if we can solve for t, that's time. We'll know how many it is. So like before, if you have a variable up in the power, the way to fix it is take the natural log of both sides. Okay? when you take the natural log of an e, basically the natural log and the e cancel, and this whole right side becomes the power. ln of 0.05 becomes all of this. So to solve for t, I divide both sides by that negative 0.0001238, and that's how we get t equal to be this. Now, I'll do like I did a second ago. Let me get the calculator out to make sure you see how we calculate that on the calculator. So, natural log of 0.05. In my calculator, I type in the 0.05 first. I hit the natural log button, and then I divide it by 0.0001238, and it's a negative. So we get 24,198, and they wanted us to round this. They didn't say it, and I didn't see it at least. They rounded this to 24,200 years, but you see how we got the answer, how you get that in the calculator. So that's where they come up with all of this. Okay? So now back to where we are. All right. So that's where the 24,000 years comes from. That's how you can tell how old something is. Basically, if you know what percent of the carbon is left, that's how you can tell. Okay, so our last couple here, particular person learning how to swim, distance y in feet, they're able to swim in 1 minute after 2 hours of practice, approximately by this. Okay, basically, the more they practice, they're able to get a little more distance is what's going on. So y is a distance, and this is a different formula, as you can tell, but it's going to work the same kind of way. 10 hours of practice, so we put in that and try to figure out what we get. Here's the equation. Now, where did we get this from? In this particular case, all right. Oh, they want to know the rate of improvement. So that's why when you hear a rate, remember, we're talking derivatives. So you take the derivative of this, and we get this. Now, the part, again, not shown is distribute that 50 still the original equation, and that's a t right there, sorry. Y equals 50 minus 50e to the negative 0.04t. Now we take the derivative, and you see the 50 is gone, and we get negative 50 times negative 0.04 e to the negative 0.04t. Remember your derivatives. The derivative of e is the same exact thing, and the chain rule says you got to multiply the derivative of this out front. That's why there's that negative 0.04 there. And negative 50 times negative 0.404 is where that positive 2 comes from. Okay? So now they say, when you plug in that 10 into the rate, after 10 hours of practice, what's the rate of improvement? Well, we've taken the derivative, we plug in 10, and in your calculator, you get e to the negative 0.04 times 10, so that's e to the negative 0.4. Multiply that answer by 2, and there's our 1.34 feet of practice. Okay? So nothing much except for just remembering when you see rate of improvement, rate of change, it means derivative every time. All right, our last slide just kind of summarizes what we found. If you have a positive k, your graph is exponentially growing. If it's a negative k, it's going to be exponentially decreasing, but it's not decreasing to the point of going down, down, down to negative infinity. It's just getting closer and closer to 0. So that's our two graphs, what we have right there. And then other types of growth here, summarize, look at them, you can see what's going on. We have the growth, we have the decay. Don't worry so much about memorizing these pictures, or these tables sort of summarize, but they're not the most important. Okay, I'll get to the homework now, and then we can kind of see where this all comes into play. So, pulling up your homework here, let's pick up with that number 43. And let's see if we can knock out a few of these homework problems here. Okay, so find the general solution of the differential equation. Well, what they want you to do is they want to know what's the original y equation. And it's general because when you have a derivative, that can work for many things. So what they're really doing here, when they say dy dx equals 7 over x, and you want to get y. Well, we know to go from y to dy dx is derivative. To go from dy to dx is integral. So we're going to integrate both of these right there, okay? Integrate the right side. Now, to make this a little bit, I'm going to do this just kind of parallel over here. To be 100% official, what you should be doing is taking the integral of both sides. And you'll see where I'm going, why I do this is, you then multiply both sides by this dx. And now you have two integrals because remember, an integral needs the d something to tell you what variable you're working with. So now on the left, the integral of dy is just y. On the right, the integral of this is going to be 7 natural log of x. 1 over x, remember, the integral is natural log of x. And then you have your plus c, and that should be what we have here. And don't forget to put the natural log of x because you will get marked wrong if you don't have that on there. If it's just x, they are going to mark it wrong. Okay, so that's it for number 43. That's all they want you to do is basically take the integral of both sides. All right, let's look at 47. All right, give the order of the differential equation below where y is represents a function. Remember how we find the order? Wherever the highest number of derivatives is, I see a second derivative here, so it looks like first order, no, third, second. Looks like it's second because the second derivative, no higher. And that's all there is to that one. So don't stress about something like number 47. All right, now we get to some of these with a little more guts to them. Find the general solution of this equation. Okay, so in this particular problem, they're going to tell you a process, but I'm going to pretend like, okay, well, how do you know when to do it? Let's pretend we don't know. Let's treat it like the last problem. This is what we have. If I was to integrate both sides, and then remember last time how I multiplied by dx, I get this right here. Now the problem you need to see is, wait a minute, I've got a dx, but I got the y with it. You're not supposed to have the y there, okay? So how we get rid of it is, we're going to multiply both sides by 1 over y, or you can simply divide both sides by y. And what that'll do is that'll make this cancel. Now we put the y where it belongs in here. And I shouldn't have put it out front, but I'm just showing you right here. They have it like that. And now you have integral of 8 dx. Now you have two integrals you can do. Now, you shouldn't really do that before. What you should be doing is whenever you see a y here, you should take care of it right now. Move the y over before you integrate it. In the end, it's not going to matter, but that's the technical way you should do it. So now I move this up to the top. I have a natural log, natural log of y equals 8x plus c. Okay? Now they want the equation, notice, to be in a y equals form. We have an equation right here. We have a general solution, but we need to solve for y. So that's our next part. And it's nice that they give you a hint by this over here. It's not always obvious because you do have a general equation, but now we have to figure out where we go next. And this is one that I did earlier in the homework. Remember, if you have a natural log of something that you want to get rid of, the easiest way is make it the power of an e and do that to both sides. And that'll make this cancel with the natural log. So on the right side, you get just absolute value of y equals e to the 8x plus c. Okay, then if you remember what we did earlier, let's split this into e to the 8x times e to the c. And then depends on the problem. When you have an absolute value equal to this, okay, y could be either of these, but if you have a potential possibility of being a negative, the way to get rid of this absolute value is simply, let's just put a plus minus out in front here. Now I'm going to rearrange these for one reason. I'll show you in a second. Now, We don't have to have a plus c. We already had it. We still have to keep the c here. And I'll show you this right here. So you may be wondering, oh, what happened to the e? This right here is a constant. E is 2.7. C is some mystery constant. We don't know what it is. But whether we call it that what's in a box, or we can simplify and just say it represents some constant. I don't know what it is. We don't really care. But if you can make it, like c plus c is still a constant, just call it a single c. Okay? 2 times c is still a constant, just call it plain c. You can condense things. So that's where I'm getting this answer right here, and that's the one that I'm going to try to plug in to this equation if I can right here. So we have the plus or minus, and I think you have a plus or minus in here somewhere. The plus or minus, really, remember, is just to get rid of that that idea of the absolute value here. Okay, so if we have to, we can just do all right. I'm not seeing a plus minus. I swear you guys had a plus or minus. Let me do this. Okay, x can be anything, constant can be anything. I wanted to put that plus or minus, but I don't know if I am just blind to it right now. Okay, let's try this. Let's see if I can just do a... That's not going to work. Okay, oh, I know what it is. Sorry. When you have a c in front, c inherently could be positive or negative. You don't even need this plus minus anymore. You could just call it all one big c. That's what I'm going to try and see what happens here. All right, and that's what it was. So yeah, normally to get rid of the absolute value, you got to put a plus minus over here. But since that's a c, and c can be anything, it doesn't, because say c was a 9, doesn't have to be a plus or minus here. It can be any of those. It accounts, it encompasses them all. So that's the process you're going to do to get this one. My suggestion on a lot of these is you're going to see me do one of these. When you get to them, if you're not sure, do not be afraid to click, where is it? View an example. You'll kind of see, hopefully it'll be something like what I did here. Let me clear this out and show you what I mean. If you haven't been already doing this, see, the problem what we had was dy dx equals 8y. They have dy dx equals 5y, and they sort of walk you through how to do this one. See, here's that multiplying by 1 over y, then take the integral of both sides, then move the dx over. They didn't even do that, actually. They left it out, which is fine. Oh, yeah, the dx is right here. So it's very similar to what I did, same kind of thing. And then in the end, they solved it the same. And you see they had that e to the c like I had. And then there is that plus or minus, and then that whole thing becomes a regular c. And that's it. And that's how we got the answer. So you see it's the same kind of thing. But this will definitely, they walk you through these steps. If you click on the help me solve this, it'll do this problem. But then when you're done, it will regenerate and give you a different one. So it's going to start all over. So my suggestion always is try the view example to start, just to see how that works. And then if you get stuck, then do the help me solve this. Okay, which slope field is associated with this derivative? Okay, now remember, we kind of did one the other day, or earlier today. There's only a y. So, and let me zoom in a little bit just so we can see this a little better. Maybe. Okay, so there's only a y, and the idea is when you start plugging in different y's, what kind of slopes do you get? Okay, so let's start with the easiest one. Let's plug in 0. When I plug in 0 for y, I get a slope of 1, which is slightly higher. Now, I don't see any slope field on this one, but I kind of see one here. I kind of see one here. It's not telling me a whole lot. And notice it's 0 for any y. If you want to get real specific, let's just call it a point. Let's do the point 5, 0. Not too big. Let's try 3, 0, sorry. So we don't go off screen here. So 3, 0, when I plug it in there, that gives me a dy dx, or a slope of 1, because I replaced the y with a 0. So at the point 3, 0, there should be a slope of 1 right there. Here it should be a slope of 1, and over here it should be a slope of 1. Now I definitely see it here on this picture, but I can't really tell too much on the other sides, so that's why we get more points. Let's go get the point, let's say 1 comma 4. So when I plug in 4 to this same equation, I get a dy dx of 5. So I get a slope of 5. That's a pretty extreme one, and that one looks like it is. This one kind of looks like it is. This one does not look like it is. It looks like it's back to a slope of 1, so I'm going to get rid of this one. Okay, so it's between these two. Now, as I was doing it earlier in the problem, when you have no x right here, it should be the same slope all the way through. See how these are all pointing in the same direction? These are all pointing in the same direction by line by line. So these graphs both look good on the left. We just have to figure out which one is which. And if you kind of look at it closely, if you dive in a little more, see how they're very high slopes right here? And then they start getting flatter, and then they start pointing down. So what I want to see is, well, where is it at 0? And it looks like here is a slope of 0. Over here, hard to tell, but it looks like my 0 is right here, somewhere around here. So how do we find that out? Well, let's try another point. How about 0, -1? And when I plug in -1 right there, I get a dy dx that's 0. This one looks like my 0 is right in the middle. Here it looks like it's at -1. This should be our picture right here. Okay, so it's just a matter of you plugging in some different points and seeing what slopes you get and which one matches the most. So let me zoom this back out if I can. All right. Oh, I did click it. I don't know why it didn't let me do it. I guess I clicked that by accident. Sorry about that. So this is what it does say. That's our answer right there, but that's the one. Okay. So let's look at 59. All right. Now we get our population growth here. What's the correct year? They're asking, let's see here, denote the population of a certain country in time t. 1965, it was 3.6 and increasing at a rate of 2.5. 97, it was 6.3 and increasing at a rate of 1.8 per year. In which year was the rate of growth with q with respect to t greater? Okay, this dq dt. All right, so how are we going to do this one here? I can kind of see the answers. You might be able to see the answer when you're doing this, but let me show you something here. How we're going to do this. Okay, so what we have to look at is it's like there's two separate problems here. 1965 and 1997, and I'm not going to be able to fit it all in here, so it's going to get me a lot of erasing, and feel free to rewind and go back if you have to. What's going to happen though is we're going to get that same equation with the ERT that looks like this. And remember, the Q with the 0 is the starting amount, the R is the rate, the T is the time, and then the Q is the new population, the current population at a given year after so long. Okay, so the first step is in 1965, treat this, like I said, like two different problems. In the problem on the left, my equation is going to read that, make sure I'm getting this, 3.6 million. That's my initial value, E, R, and it's at a 0 right there. Okay, the time is 0, so I'm getting a big 0 right there, but not going to worry about that right now. All I want to know is that I'm plugging in place of the initial is 3.7. Over here, the initial of 1997 is going to be 6.3 e to the RT. Okay, that's kind of, you're always going to be given some sort of a basic information to help build your equation. This is the equation right here, and then we have to use what they tell us. And like I said, we're treating this as two different problems. So what's going to happen is we're going to look at the rate of increasing, what we're getting here. And you're going to find that the rate, and this is a kind of a given formula I had earlier, dq dt equals R times Q. And that's going to be the case in both problems. The rate that we're looking for right here, this dq dt, what you have to remember is it's always going to be the rate times the original. So what we want to do is we want to find what happens as this thing grows. So we have an R. In place of Q, I'm replacing all of this. Okay, and they also told us the rate. Let me get rid of that. If you remember, for the 1965, the rate was 2.5%. So I'm going to replace that rate with a 0.025. And I'm going to replace Q with this box right here, which is 3.6 e to the same rate, 0.025. And what we're going to do is we want to see what happens when they want to know the growth rate. We want to find from 1 year after. What happens a year after? What's it going to be doing? What's the speed? How fast is it changing in that same year? So we do the same thing over here. dq dt equals the rate of growth in 1997 was 1.8, so we get a 0.018 here. Replace Q with all of this times 6.3 e to the 0.018 times, again, the 1. What's going to have to happen after 1 year? So in both cases, and I'm going to get rid of this just so we can have a lot more clean space to work on. So we're going to go in our calculator and punch in both of these. Okay, and I'll see how well these turn out. So this one on the left, we got a lot happening here now. It's just 1 times 0.025. So all we need is the 0.025. Find that to the e, multiply it by 3.6, multiply it by 0.025, and we get this. This is our rate of growth, 0.09227. I'll stop there at the 8. Then we're going to do the same thing over here. We take the 0.018 in the power. That's your power of e. Multiply it times 6.3. Multiply it by 0.018. And we get this 0.11. So this is essentially 9%, 9.2%. Let me just kind of round that right there. This one is 11.5%. And that's all we need to know. Which one of these is growing faster? Well, it's going to be the 1997, I think. And that's it right there. That's our official way to tell. Okay, now notice it's not enough just to say, well, this has a bigger rate. Or no, in fact, you notice it didn't have a bigger rate. 65 had a larger rate, but because the population was so much smaller, it wasn't having as a big of effect as this other one was. So that's why you have to go through this process. But literally mimic this, and I believe if you look at that view example again, it will really walk you through this so you get the hang of it. And it's not that bad once you see how, these start to work out. Okay? And lastly, let's go to number 63. Get you through this one and then be done with this homework. And we have a carbon-14. Okay, good problem here. Bones lost 17% of its carbon-14. How old is the bone? Okay, exactly what a scientist would do is what we're doing right here in this particular problem. So we have, this is our formula. Okay, so this is the given right here. And they tell you it's lost 17% of its carbon. Now, the T, so you know, this is what we're trying to find. They ask you, how old is the bone? They're looking for the time. So don't worry about trying to find something to replace that. You got to replace everything else. So since it's lost 17%, that means it has 83%. Okay? Notice that they word it differently sometimes. The other one, they told you had 5% left, so we put in a 0.05. Here, they tell you it's lost 17, so you have to do that quick math, subtract it from 100 to know that it's got 83% left. So this up front is going to be 0.83 P naught, P sub 0. And now you can divide away the P naught, and then we have 0.83 equals e to the negative 0.0012t. Like I said before, if you're trying to get a variable out of a power, you natural log both sides of it. And that makes the natural log and the e cancel. So I have natural log of 0.83 equals negative 0.0012t. And then last, divide both sides by this negative 0.0012. And that makes it, all of this is equal to t. So our only final section to do here is I need to go and plug all of this stuff into my calculator. So I have the 0.83, natural log that, and then divide it by the 0.0012, and we get 155. So round to the nearest integer, it should be 155 years old. And oh, what did they get wrong here? Let me look. Okay, not taking me too long to find it. Let's see what it is. Gotta read your original problem. If you notice that equation, it's got 3 zeros. 0.0012. So there should be 3 zeros here every time, which means I just need to divide by 3 zeros down here. Let me just rewrite that on the bottom. So we're all on the same page here. Negative 0.00012. And of course, that's going to have a huge effect on what our final answer is. So let me get the calculator back up here. And try this one more time. I can already tell what it's going to be, but show you guys. Don't have to do this in your head. Natural log of 0.83 divided by 0.00012. And now we get 1552 years. Round that to the nearest, so it should be 1553. And now we have our answer. Okay? So this should take you through all of these homework problems here, I believe. So if you have any questions, shoot me an email. You should be good with 5.2, 5.3. Next week, our final week of the semester, we'll do sections 5.4 and 5.5, and that'll be done. So look for a couple more lectures early next week, and then I'll kind of have a quick rundown of what's going to be on the final in that last video, or I'll record a separate one for that. So until then, again, shoot me an email if you have a question. If not, good luck on everything. Do your homework. Get your quiz done by Monday night like always, and we'll get into that last week. All right, have a good one.